Ready to start? Okay, ready to start? Okay, I put results for the mastery exam number 2 up, and I explained the whole thing on Blackboard announcements, and then I put some current course overalls up on Blackboard announcement or on Blackboard grades, and I put details on the announcements for that as well. So I'm not going to go over that. It would take at least 5 minutes to talk through all that. So just read those 2 announcements very carefully, and that should clear up most of the questions. But if you still have questions, then you can email me. Okay? So some of you are required to take a 3rd mastery exam. Some of you might opt to try for higher grade. All those details are on there. Okay, so we want to talk about start talking about Optimiz. All these things that we're doing, inferring things about the accumulation by looking at the rate of change, is one application of that is optimization of the accumulation function. So how does the following table relate to the accumulation's optimal values? So first of all, what do we mean by that, optimal values of accumulation? What does that mean?
You mean in terms of positive numbers and negative numbers?
Okay, so is that talking about positive or negative values of accumulation? Optimal values. What do we think of when we think of optimizing? Just negative and positive?
Like high points, like if you were trying to maximize profit or minimize cost.
Okay, yeah.
Like that.
Yeah, so maxima, and minima. So when does the accumulation reach a highest value? And what is that highest value? And maybe it's cost or golf score or something that we want it to be the lowest possible. So when does accumulation function reach a lowest value? So what does this table have to do with that? Finding values of the accumulation that are the greatest or the least. So lots of people are not paying attention. Lots of people are looking at your computer, looking down. So is everyone here with me today? What does this table have to do with maximum or minimum values of the accumulation? Why don't you talk about that with someone next to you? Talk about that. What about this table would have to do with that, finding maximum or minimum values of accumulation?
That's just at the lowest point. I
Okay, what do we think? Melody?
I thought it would be relating the first derivative positive first derivative negative.
All right, so what was the first thing you said?
The top left square.
This one?
And then the kitty corner, not the nope, that one.
All right, so she's saying that this first row helps us to determine where the first derivative is maximum or minimum. Agree with that? Alexander, you agree with that? Has to do with the first derivative being positive.
Yes.
Okay, and what does the first derivative being positive mean about the accumulation?
That means that the accumulation function is increasing.
Increasing, right? So everything in this first row is, the accumulation is going up. So what about optimization? Finding a maximum or minimum value of accumulation. Is that going to help us? the first derivative is positive? Kevin?
It's when the first derivative equals 0.
He wants when the first derivative is 0. What does it mean for the accumulation in general when the first derivative is 0? What does that mean?
Pauses.
Pauses, right? Accumulation. Pauses. That's our first derivative equals to 0. Is when that accumulation pauses. And how does that relate to?
To maximum.
Yeah.
Well, if it's, I'm just gonna fill like what I have over here.
Okay.
If the second derivative is positive, then the graph looks like that, which is the local range.
Okay.
And then, so, that way, like, you're looking for optimization, which is like the optimal point, as
Right.
like the maximum or minimum.
Okay.
That would be your optimal min at that point.
So this is the optimal min.
Now that's the local min, but there could be your optimal min.
Okay, so this is the local min.
Yes.
Christian.
Wouldn't the bottom, like the lowest point in that, be the local min?
Yeah, there's only one. So in terms of the first derivative being 0 or the accumulation pausing, there's a very specific place that happens, right? And that's where the accumulation stays constant for just one moment there. And then similarly, if the second derivative is negative. So who wants to take it from there? So talk to me about optimization of the accumulation in this situation here. Jonathan.
Well, that's when you have a local maximum.
So how do you have a local maximum?
When the first derivative is equal to 0.
And that's this whole thing right here?
No, it's only one point near the peak, I guess.
Near the peak?
Or at the
Yeah, at the peak is when, again, when the accumulation pauses for a moment, it's going up, and now it pauses, and then it starts going down. Well, that's going to be your maximum value. Okay? So if we get a value of the first derivative equal to 0, do we know if it's a maximum or minimum value? What does it tell us? Are we guaranteed a maximum or minimum value?
It's only guaranteed if the second derivative isn't 0.
Right. Yeah. So that's where we look to figure out if we have a max or min, and which it is. That's when we look at the second derivative. If that second derivative is positive, meaning the rate is doing what? What's the rate of change doing here?
Becoming less negative or more positive.
Right, or increasing, exactly. So both, yeah. So becoming less negative, more positive. The rate of change is increasing, and the first derivative is 0, and you have a pause of the accumulation. You have a local minimum. And then if the second derivative is negative, what does that mean for the rate of change? All through here, the rate of change is decreasing, becoming less positive or more negative. So if along with that you have a pause point of the accumulation, that has to be a local maximum. So the first thing we're going to do is we're going to find those places of pause of the accumulation, which is where the first derivative is 0. And then we have to figure out what kind of pause we have. We saw other pauses too, right? This is a pause. Okay, so let's do some practice. So this is where we're going. We're going to talk about how do we use the first and second derivative to figure out where a quantity function or accumulation function has a highest value or lowest value. That's kind of what we're after here. So I want you to practice with this and see how this is kind of putting lots of stuff together here. So consider this accumulation function. For each of these x values, I want you to find the current value of accumulation, and then find appropriate values to determine how the accumulation is changing. Express your conclusions with words, no graphs. Okay, so don't graph this on graphing calculator or your handheld calculator. This is just a numerical exercise. And from the numbers, we're making conclusions about how the accumulation is changing. Okay, so take about 5 minutes to work on this. Okay, so just from values, and I'm not telling you what values. So that's hopefully since you're putting some things together, some different tools that we have, determine how the accumulation is changing at each one of these x values. Okay, go. You can work together, and I will. If you can. Still show all that. That's fine. I'm going to take roll. Show me your work so far. Have you learned anything? So this is kind of putting together lots of things we've learned in the course. Functions, stuff we've done recently. Can you put it together? So no one's really gotten to the work part of this yet. All right, so let's. So you're all focusing on the accumulation. So let's just get those values. Let's just write them down here. What's the accumulation of 0? So we can get going. 3.5, 1.313, 1.5, 2.8, 1, 2, 3, 6, 2. Okay, so we're done with that. Now the important part. Got the accumulation at each of those x values. Stop working on that. Now part B, the important part. Okay.
If it's going less, like as it's going
Written descriptions of what's happening.
this is 3 and then somewhere.
One word side of 0, right? So here's a couple homeworks, but you're just gonna they're grouped together. So once you get one stack, that's 2 homeworks. Don't look, they're put together. Alphabetical by last name.
I think you're right. You first triggered it at 0, it's negative 8, it's decreasing, and then the first derivative is at 0. Yeah. No, I took the derivative of the accumulation, so it's 8, and then it tells you, and then you do the second derivative to find the rate.
Okay, so I think most of us figured out that we want to take the derivative of this, right? So let's get, and then we're going to find, say at 0, what is the value of the derivative?
I got -8.
Negative 8. How about at 0.5?
0.
1.5.
1.
2 is 2?
Yeah.
6? Anyone get 3? Or 0 again?
0.
Okay, so potential places of a maximum or minimum, or an optimum value of the accumulation. Where are the potential places for that? 0.5 and 2, right? So we're looking for a pause. If we're looking for a max or min, we're looking for a pause, and that's where we have a pause. Okay? If we want to know more than this, so, and then we could say like at x equals 3, what's happening to the accumulation? How is the accumulation changing at x equals 3?
It's increasing.
It's increasing. All right, is that true? Can we do better than that? Just from what I've got up there. So can we be more specific than it's just increasing? How is it increasing? Okay, so Christian's saying we can't know anything more than just that it's increasing. Does anyone think we can know something more from the first derivative than it's just increasing? Please, somebody know this, or I'll be sad. What does the value of the rate of change being 10 tell you about how the accumulation is increasing?
It's like a pop that's going.
Alexander,
Tell us about fast.
and tell me.
So if the derivative is greater, it means accumulation is increasing fast.
So tell me about 10 at x equals 3. I'm sorry, is that x equals 2? Sorry. Yeah, no, x equals 3. At x equals 3, we said that the accumulation is increasing. Can we say any more?
It's increasing faster than x equals 1.
Okay?
For a small change in x at x equals 3, y is increasing at a rate 10 times the change in x.
Saying y is increasing at a rate 10 times the change in x. Around, yeah, right. So that's what we've been working on all semester. What does rate of change? What does that value of rate of change mean? It means how fast y is changing relative to x. So for a small change in x, y changes 10 times as fast as x changes. And what about at x equals 0? So Zoe, what does that negative a mean?
Means that for every little change in x at x is around x is 0,
Yep.
that y is changing negative 8 times the change in x.
Good. See that? So around x equals 0, for a small change in x, y decreases 8 times as much as whatever change in x you picked. Okay, around 0. Good. So now we want to look at second derivative. Anybody got them? At 0.
Yeah, 24.
24?
9.
9? Negative 3?
0.
0?
24.
0. Okay. So who can tell me at x equals 0, can you articulate how the accumulation, so the accumulation has a value of 3, but how is it changing? Anyone articulate how it's changing? Christian, you want to try?
Well, since the first derivative is negative and the second derivative is positive, that means it's becoming, it's kind of going like down like this, and it's becoming less negative.
What's, so no, you can't use it. Sorry.
Sorry.
It's good.
So that means that the rate of change is becoming less positive.
The rate of change is becoming less positive. What do you think? That would indicate that the rate of change is positive.
I mean, what's it called? It's going like this, so it's becoming less negative.
Yeah, so the rate of change is negative, which means that the accumulation is decreasing. And how is it decreasing? Is it How is it decreasing? How can we put that into words?
Less negative?
Okay. So we get, yeah, when the rate of change is decreasing, we really have to, it's really have to watch our words. So the rate is decreasing, or sorry, the accumulation is decreasing, and the rate is doing what? Increasing. So what does, if the, that, or becoming less negative. So the rate, we say the rate is increasing, because the second derivative is positive, or becoming less negative. And so what does that look like in terms of the accumulation graph? Draw it with your finger. Should have drawn this. And at the very value of x equals 3, y is decreasing 8 times as fast as x, right? Y is decreasing 8 times as fast as x. But that rate is becoming less negative. That rate is becoming less negative as indicated by the 24. Okay, tell me about at 0.5. Somebody new. Connor, can you explain what's happening at 0.5?
It's going to be increasing at
No, it. And keep them separate, okay? Keep each thing separate.
accumulation will be increasing at a positive rate.
Accumulation's increasing at a positive rate. You agree with that, Aaron?
No, the accumulation is not increasing, it's a amount of 1.31.
Okay, but so tell me how you got there. So can you explain, so what's happening to the accumulation, first of all?
It's paused.
It's pausing. And then so this tells us how the rate is changing. How's the rate changing?
It's positive, or a positive rate change.
Well, but you just told me it was 0. This rate of change is 0. What does a 9 tell us about the rate of change?
That the rate of change is increasing.
Increasing, right? So it's increasing. So if we had a pause with a rate of change increasing, what does that mean? Brent,
The change in concavity.
there's a change in concavity. Is there a change in concavity at x equals 0.5? David, what do you think? So we have a pause, and our rate is increasing. We have a pause, and our rate is increasing. He's drawing a picture like this. So all along here, is that what you're talking about? All along here?
Just at the point 0. Oh, 0.5.
Where is 0.5 along here? See, this is many x values.
At the
Very bottom. So right there is where our accumulation pauses. But all the while, what's the rate doing? Through the whole thing, increasing. The rate's becoming less negative and more positive. So along with a pause, that gives us local min, which is what Aaron said. Okay, let's look at 1. What's happening at 1? Tell me what the 2 means. This, Connor. So what does the 2 mean for x equals 1?
Yes, value is changing 2 times as fast as the y value.
The x value is changing 2 times as much as the y value. What do you think about that, Danny?
I think you meant it the other way, where we're changing that point. But either way, the rate's positive, so the rate's positive for first derivative.
Okay.
So it's in the second derivative.
So tell me about the accumulation then. So what about the accumulation if the rate's positive?
Every change in, is it every change in y, the x value changes 2 times as much?
Uh-oh, it's contagious. So for every change in?
Every change in y, the x value changes 2 times as much?
Yeah, that's what Connor said, and you said that was wrong, and then he was caught. You got his illness. Yeah, other way. So for a change in x, how will y change? Twice as much. So therefore, the accumulation is doing what? Increasing, and it's increasing, the accumulation is increasing twice as fast as how x changes. All right, so now we're increasing, so maybe that looks like this. But then what does the second derivative of 0 mean? Steve?
Means the rate of change is paused, so there's a constant rate of change at that moment in time,
So
at that current x value.
Right, and so there's two ways that could happen. It could be, the rate of change could be increasing and then pause and then decrease with a rate of change of 2, or the rate of change could be decreasing and then pause and then increase with a rate of change of 2. Does it make sense? Okay. Anybody have a question? So let's, what's happening at x equals 2? The first derivatives are 0. So the first derivative 0 means that accumulation, Shannon, paused. And the second derivative 0 means that changes direction. Okay, so remember, this is our situation where it's kind of like there's lots of different things that could be happening here. The jury is out. When they're both 0, one possibility is that there is a change of concavity and a pause at the and an accumulation pause at the same time. That's really hard to draw. I can never get that right. Let's see if I can do it. That's pretty good. This is one possibility, or this is another possibility, but there are other situations that could happen. This is kind of the most common, where you have a pause and then either keeps increasing or it keeps decreasing, and you have a change in concavity. But there are other. This isn't the only thing that could happen. Yeah.
Is there any way to know from the information we have, or do we need?
We need to do some more. So we would need to look at maybe x values just less than 2 and just greater than 2. And look at what their first and second derivatives are. And that could really help us pinpoint what's going on. Okay, any questions on this exercise? Okay, so with optimization then, so here's another function. So now based on what we just did, can you find relative maxes or mins or inflection points from the tools that we have? Okay, so here is this function. Can you locate now I'm not giving you the values of x. I'm saying, can you find values of x where j has a high point, or j has a low point, or j has a changes concavity? See if you can do it. Work together. How's the homework going around? Where's the homework at? Homework stack. Did it go by everybody? Did everyone see the homework stack? Thank you. Shannon, did you get a start on this? Okay. So you found, what did you find? And what is that you found? What did you derive? The equation of what? You said, what did you say? Okay, so it's important that we have good, meaningful language for what that is. I'll try one more time. So, in a meaningful way, can you tell me what that function is or does? First derivative, okay. Remember when we first start doing derivatives, we said we always wanted to call it by what it was. Yeah. The rate of j, the rate of change of j with respect to x, right? The rate of change of j with respect to x. And so, what about it? Let's see. Kaylin, why would we do that? Did you do that?
Yeah, I did.
Okay, and so how does that help us with this situation?
Let's see. Well, if we have a set of x values, we can plug those in and find y values for the accumulation function, and then if we plug those same x values into the derivative, then we could describe how the accumulation function is changing.
Okay, but we don't have a set of x values.
But we can make a set of x values.
Okay, so it's kind of like you're gonna just start guessing x values.
Yeah.
Do we need to do that? Okay, Aaron.
Don't you, you said your g of x is 0 because that helps you find the critical points which will help to figure out your maximum or maximum minimum.
Right, so what do we, yeah, exactly. What do we know about the accumulation at a relative max or min? What happens to the accumulation?
Your function is set to 0, so
What happens to the accumulation at a relative max or min? Pauses. And if it pauses, then what about the rate of change? 0. So yeah, so we're gonna look for locations where that rate of change pauses, and a pause means the rate is 0. Accumulation staying the same for a moment. And so we got to remember our algebra skills, right? What is that? X minus 5. Did I? Oh, and I screwed this up. Sorry. I factored out a negative, but then I didn't do it. This should be minus, and it should be plus. Now it works. Sorry. Does it work? And so we have x values that do what? Those x values don't equal 0. Christian, sorry. Make the rate equal to 0, right? Those x values make the rate equal to 0, so we have places of a pause of the j function, of the accumulation, which are potentials for max or min. So one of them's a max and one of them's a min, and we just got to figure out which is which. Is that right? One of them's a max and one of them's a min, and we just got to figure out which is which. Is that right? Chloe? Yeah, so remember that just because it's a pause doesn't necessarily mean it's a max or a min. Neither of these could be, it's possible they could both be, this situation. Or this. Okay? So it doesn't, we're not guaranteed anything. So how do we know for sure?
You need to know the rate of the rate.
The rate of the rate. So tell me that.
So you take the derivative of the rate.
Okay.
And you get 18 minus 6x. And then you look at the rate of the rate at those two x values.
Okay. So he wants to look at this. Now this is what you're doing in the previous exercise. What is the rate of change at x equals 5?
Negative 12.
So conclusion, at x equals 5? What's that? Why is it a max, Steve?
Because the second derivative is negative.
Which would mean?
It's,
So the rate.
the rate is decreasing.
Right. So this tells us that at x equals 5, what? We have a pause in the accumulation, and the rate of change is decreasing. So it must be concave down, and therefore at x equals 5 we must have local max. All right, and then we can do it at 1. What do we got?
12.
So at x equals 1. He wants a local min. Why is the local min, Nicholas?
So yeah, the second derivative is positive.
So what is
The function's pausing, but it's also increasing. Or the rate's increasing.
the rate is increasing all through there. The rate is increasing, and the accumulation is pausing for a moment. Accumulation is pausing for a moment because the first derivative is 0. The rate is increasing the whole way. So we have a local minimum. The rate's becoming less negative and more positive. Okay, so any questions? So this is kind of our approach, really understanding what the first and second derivatives tell us, and then if we want to locate relative maxes or mins, we're going to say, okay, we want that accumulation to pause, which means we want that rate of change to be 0. What values of x make the rate of change 0, and so therefore make the accumulation pause? Those are our candidates for relative max and min. And then we can use the second derivative, and we understand what's going on with the second derivative. It tells us whether the rate is increasing or decreasing to pinpoint whether it's local max or local min or something else. Okay, so we're going to be doing lots of application problems of these, some of which will involve angle and trigonometry. So I want to give you a crash intro course in trig and angle, okay? And we got 8 minutes to do it. Are you ready? Okay, so I've got 3 circles here. And I just put a purple bar up. What am I showing by that purple bar right there? And can you read what the radius is? That circle has radius 1, so I'm showing the radius circle 1. So that's the conventional place, but I'm going to peel that off its normal place. I'm going to wrap it on the circle. So how long is that arc now? It's still 1 unit. It's the same. It's the radius wrapped on the circle. Okay? It's the radius wrapped on the circle. Okay? How about the next circle? Can you see what its radius is? 4. Okay, so again, now this is the blue one. I'm going to take it off of its normal place. I'm going to wrap it on its circle. How long is the arc? The arc length is 4. Same thing. Can you see what the radius of the last one is? 6. Wrap it on its circle. Okay? So, what's something that you notice that's the same about all 3 of those arcs? They all have different length, obviously, 1, 4, and 6, but there's something all the same about them as well.
Do they have the same arc length relative to the other circles?
He's saying they all have the same arc length relative to their own circle. Okay? And so that's a basis of forming an angle. So they all mark off the same percentage of their own circle, right? Okay? So that gives us a consistent way of measuring angle. We can measure angle by what we call relative arc length. So since these are all they're all different lengths in terms of the units of the axis, but they're all what? All of them are 1 radius length. This is the key to angle. All of those are 1 radius length on their own circle. And so an arc length of 1 radius length, no matter what circle you use, marks off an angle of what we call, that's where we get radians. That's 1 radian of angle measure. Okay, so I can extend that to 2 radius lengths. So here's 2 radius lengths right there. And they still all give us the same relative amount of a circle. And so this angle then is 2 radians. Okay, so the openness is 2 radians because it's the angle that cuts off 2 radius lengths. Okay, so now I want to put it at 3 radius lengths, and then I'll have you make a. So there's 3. Okay, so this is now showing for each circle it's showing 3 radius lengths, and so for each one I want you to. We're going to make a table here. So for the purple, you're gonna do this, and for the blue, and for the red, I want you to do the arc, the radius. So what's the length of the radius in the units of the axis, and then what's the length of the arc? That's arc length, and then what's the angle measure? You're gonna make a table. Go quick so we can get through this. Is the task clear? Do those symbols make sense? R is the radius in the units of the x-axis. S is the arc length. Let's do it the other way around. Sorry, let's do theta next. Theta is the angle measure in radians. And then S is the arc length in the units of the x-axis. Okay, go finish this table. Check with the people around you.
At this point,
Yep, I've got 3 radius lengths. So this is for this what I'm showing you right here for 3 radius lengths. What the angle is. That's what we talked about here. So where does that angle come from? Does that make sense? So for the purple one here, so if this is 3 radius lengths, what angle is that in radians? He wants 3 radians. Look right here. So the number of radius lengths that's cut off by the angle, that's the angle measure in radians. So this is here, this one here. Don't pack up and go away, please. We're not done. This is 3 radius lengths. So what angle is it? You're thinking too hard. You're thinking it too hard. This is 3 radius lengths. So what angle is it marking off? 3 radians. This is 3 radius lengths. So what angle is it marking off? Okay, so let's hopefully finish the table. Purple. What's the radius? What's the angle? 3. What's the arc length? Blue. 4. What's the angle? Arc length. Red. 6. Okay. This is going to be cool. Ready? What does theta equal? How can we calculate what the angle is?
Arc length over radius?
Right? It's arc length over radius. And what does a quotient, in general, what does a quotient give us? Remember what, from the first week of school?
Proportion K over size.
What's that?
Relative size of arc length.
Relative size. Relative size. In this case, relative length. The length of what? Relative to what?
So the length of the arc relative to the radius.
The length of the arc relative to the radius. Or in other words, how many radius lengths? That's what a radian is. It's the relative length of the arc length to the radius, or it's counting how many radius lengths the arc marks off. That's what a radian measure is. Relative length. So when you start working with these in problems, the angle measure is equivalent to a length measured in equivalent to number of radius lengths. So you can think of that whole formula that involves angle. Everything's in terms of length, right? The length of the arc in these units, the length of the radius in these units, and then how many radius lengths. How many radius lengths is what your radian measure is. And we're gonna see this coming up in some of our examples, so it just needs to make sense. Okay, thank you.